Previous class we were stopped that we were discussing for strong electrolytes the graphs is comes like this, and for weak electrolytes graph is comes like this. And we also discussed that strong electrolytes, what I've discussed that due to it is already completely dissociate, so since uh, lambda m value is already high because it already completely dissociate, so the change after dilutions, here dilutions is increasing, so after dilutions only very less amount of lambda m value has increases, whereas for weak electrolytes, so since this is weak electrolytes, before dilution this lambda m value is very less because it is partially dissociate. So after dilution, since water molecules, the ions of water molecules comes to the solutions and they do the, due to their movements, lambda m value increases, so this value increases in a huge amount. And what I have also discussed that we have take here lambda m, and generally we plot the lambda m value, sorry, molar conductance with concentrations and with, so we have decreased that on dilutions. On dilutions, molar conductance and conductance is increases. So we generally study for molar conductance only. Conductance we will not study because this is not specific. So and kappa is decreases on dilutions. Okay, so generally we studied only this graph. So this graph is looks like this. But why this graphs is look like this? For strong electrolyte this, and for weak electrolyte like this. So that we will discuss today. So for discussing about strong electrolytes, so strong electrolytes, but the two effects we have to study. One is asymmetric effect, another is asymmetric effect, another is electrophoretic effect. So due to this effect, that graphs will look like this, and we know that on dilutions this value h increases. So obviously this value is increases, but why this graphs looks like this? For that we have to study asymmetric effect and electrophoretic effect. So what is asymmetric effect? So electrophoretic effect and asymmetric effects. First we will discuss about electrophoretic effect. Let's say that we are taking like this. Yes. So let's say any electrolytes is present here. So in this electrolytes, what is that? Let's say Na plus, we have discussed Na plus, Cl minus, Na plus, Cl minus. For strong electrolyte, we are discussing about a strong electrolyte. So let's say strong electrolyte NaCl. So NaCl dissociate into Na plus plus Cl minus. So this ions is present like this: Na plus, Cl minus, Na plus, Cl minus, like this it is present. Okay, so this is before giving electric current. This randomly it is present before giving electric current, means before battery. So you are giving current from battery not connected. Okay, or I can write here battery not connected. Okay, so now what happened, that it means this graphs I can draw this way, that here, that suppose say this is like picture wise I draw like this, but actually let's say I'm drawing that Na plus as positive charge and Cl minus as negative charge. Then what it says actually, so positive and negative always attraction is there. So if any positive charge is here, then around a positive charge must be negative charge will be there, because they have the attractions. Yes, and if this is negative charge is there, then in negative charge definitely positive charge is like this. Yes, so if negative charge is there, then definitely positive charge is there. So similarly, like this whole, this is filled like this. So positive charge, then negative, then positive. So like this hole is present like this. Okay, this is before connect battery. Then what happened, whenever I connect to the battery, electric current given. Electric current given. So if electric current given, then let me draw. So if electric current given, electric current given, I mean what it means, that here I connect the battery. So sorry, here rods is there, right? Sorry, here rods are there, here rods are there, but now battery is connected. Okay, so now in this rod, what I give the electric current, that means I attach the battery. So if I attach the battery, then this is positive side of battery and this is negative side of battery. So this will come to be positive charge and this comes to negative charge. Means this electrode rods become positive, positive, positive. So become negative, negative, negative. So this rod is positively charged and this rod is, this is negatively charged rod, and this is positively charged rod. So now the ions are there. So previously what happened, previously if one positive charge is there, then surrounded a positive charge, negative charges are there in symmetrically. Okay, so first let's first discuss about asymmetric effect. Asymmetric effect, then we will go for electrophoretic effect. So asymmetric effect, so first this positive charge around the negative charge there in a spherical way, and if negative charge there around of positive charge were there, so in a spherical way they are present with each others. Whenever you give the electric current, then what happens, this positive charge attracts negative charge. So here if a positive charge, negative charge surrounded around positive charge, and this rod is positive charge, then this positive charge rod, but it will attract the negative charge towards itself. It means what happened, it means this symmetric sphere will break. So this symmetric sphere will break. So if this positive charge is there, then here if sphere is like this, then all negative charge will be comes like this. Here no charge will there, every negative charge comes in one side. Okay, so because this positive charge attracting this negative charge towards itself. So if positive charge attraction, and similarly here negative charge rod is there, negative, 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 and this positive charge is getting attracted towards here. So this positive charge wants to move to this rod, and this positive charge, again this negative charge is attraction towards this positive charge, and negative charge again they are attracted by this positive charge. So in this way the symmetric spheres breaks into asymmetric sphere. Okay, now this positive charge has to move to that negative rod, that is cathode, and this is anode. So this positive charge will move towards the cathode. So while moving this positive charge towards negative charge and this negative charge towards the positive charge, due to the ions, like this positive charge gets attracted by negative charge, so the movement of positive charge towards cathode is little bit difficult because this negative charge are attracting to it. Similarly, this positive charge, negative charge attracts towards this, also this positive charge is there, then around this also positive charge is there, so they are getting attracted to here. So this is also difficult to move towards anode. So and whenever we give the water or whenever we do the dilutions, then what happened, that the water molecules comes in between ions. It means if positive charge is there, if negative charge is there, then in between the ions, what this water molecules will come. It means that attractions between this positive charge and negative charge will decreases because water molecules will comes in between them. So whenever water dilutions is given, then the attraction between this positive charge and negative charge decreases. It means that this positive charge can easily moves towards the cathodes. Means as compared to previous, that this positive charge get attracted by negative charge, but now due to water molecules comes in between these charges, then this positive charge easily can move towards the cathode. Means the force of attraction decreases between the two charges due to water molecules. So on dilutions, this positive charge can able to move. So this effect is called asymmetric effect. So asymmetric effect, what due to dilutions is decreasing. Yes, because they are able to easily move. So due to dilutions, so what do you mean asymmetric effect? Asymmetric effect means previously whenever no electric charge is given, then this spherical sphere was there, and whenever we give the electric charge, then the spherical sphere has break and it become asymmetric spheres. So an asymmetric sphere, since this positive charge and negative charge is created by the battery to this rods, then these rods attract the opposite charges towards itself. So whenever they attract the charges towards itself, due to the charges himself surrounded by opposite ions, so the movement of the ions towards the respective electrodes will decreases. So it means asymmetric effect is high due to electric current, but whenever we give the water, then the water molecules comes in between the two charge species or two ions, so the attractions between the ions has decreases. So the charges can easily move towards their respective electrodes. So on dilutions, asymmetric effect, this asymmetric effect created by this current has decreases on dilutions. Okay, so this asymmetric effect is represented by a, so this asymmetric effect due to dilutions, asymmetric effect decreases. Okay. another effect is electrophoretic effect. Another effect is electrophoretic effect. Here itself we will discuss. Another is electrophoretic effect. What do you mean by electrophoretic effect? Electrophoretic effect, this is we will represent by B, and this electrophoretic effect, what it says that so this positive charge and negative charge is there. So in between this positive charge, if I draw the graph, if I draw again here, see, so here the positive charge is there, and in between positive charge, negative charges is there. So here we connect the battery. So this become positive charge and this become negative charge. This is positive, negative. So here, and in between negative charge, let's say this is positive charge, and here negative charge is surrounded to the positive charge, and negative charge again positive charge will be surrounded. And whenever we give the electricity, whenever we give the electricity, then what happens? This positive charge, this rods attract the negative ions, and this negative electrode, this is cathode, this is anode. So this cathode attract the positive charge towards itself. So what happened? This positive charge is moving. So this positive charge is surrounded by negative charge. Again, this negative charge is surrounded by positive charge. So this negative charge is moving towards here, and the positive charge is moving towards there. Then what happened when this charges moves to the opposite directions? Then what happened that whenever they are moving, let's say this positive charge is with negative charge sphere, and the negative charge with positive charge sphere. So this is moving here, this is moving here, then they will have some hindrance. So due to hindrance, the movement of the charges towards respective electrodes decreases. So that is called electrophoretic effect. So this effect is called electrophoretic effect. Means this charges is going towards respective electrodes, and whenever they are moving, they have to move in the solution. Through solutions only they will move. Yes, through solutions they are moving. So in solutions, this positive charge is in the sphere, and this negative charge with positive sphere, and the positive charge with negative spheres. And when they are moving, then this positive charge is moving along with negative charge sphere, and this negative charge is moving along with positive charge sphere. So whenever this positive charge sphere, let's say this positive charge sphere is moving these directions, and negative charge sphere with positive electrons around it moving towards here, then this positive and negative get attracted here also get attracted. It means they have some hindrance, because positive and negative they get hindrance. So due to hindrance, so the effect come, that is called electrophoretic effect. Okay, due to hindrance while moving positive sphere and negative sphere towards respective electrodes, the positive sphere means positive charge surrounded by negative ions, and negative sphere means negative charge surrounded by positive ions. When they are moving towards the respective electrodes, then they between this negative and positive, because in between positive the negative is surrounded, and in the negative charge positive is surrounded, so they get the hindrance, positive negative. So due to that, the hindrance that created, so that effect is called the electrophoretic effect. This effect is called the electrophoretic effect. Okay. So, and this is represented by B. And whenever we do the dilution, whenever we add the water, so what happened that this positive charge and negative charge in between water molecules will come. Okay, again the water molecules will come. So the attractions between positive charge and negative charge decreases, because previously suppose positive charge, negative charge, this much distance is there. After addition of water, this positive charge become here, negative charge become here. So in between water molecules is kept. So the attractions between this positive charge and negative charge decreases. So if the attractions between positive and negative charge decreases, then the hindrance is decreases. It means the electrophoretic effect is decreases. So B is decreases due to dilutions. Okay. So due to dilutions on strong electrolytes, both B, that is electrophoretic effect, and asymmetric effect decreases. So if it decreases, then conductance will be. So mainly we are talking about a molar conductance. So molar conductance lambda m, or equivalent conductance also, this is increases. Okay. So we previously also discussed that on dilutions molar conductance is increases. We have discussed by adding the water how molar conductance decreases. We have discussed that by taking this where we discuss. So we have discussed that on dilutions this is increases. Okay, because volume factor is dominates. Okay, so that's we have discussed. And also here also we discussed that on due to dilutions on strong electrolyte, both B, electrophoretic effect and asymmetric effect decreases, so which push the increase in molar conductance. Okay, so what happened that Onsager, Huckel and Onsager's Huckel and Onsager give equations called Huckel-Onsager equations. Huckel-Onsager equations. What he says that if you want to find lambda m is a molar conductance, then from infinity, what we have to subtract? Both B and A we have to subtract. It means B A infinity m plus B root C. So this is the Onsager and Huckel-Onsager equations, where A is asymmetric effect, and B is electrophoretic effect, and this is molar conductance. At any concentrations, and the lambda, this molar conductance at infinity, this is molar conductance at infinite dilutions. Okay, so these equations can be normalized into this A plus lambda we can get minus B root C, where B is equal to, I can write A B. Okay, so this we can simplify it into these equations, and if we plot this graph, then what we get, so this graph is, let's say we take this is y, then we can say mx minus c, because here y is equal to molar conductance, and so this will be plus it, because this concentration we are plotting the graphs, if versus concentration, then y is equal to molar conductance, and this is c, then m will be minus b. Okay, so y equal to molar conductance, and x is here root c, and m is here whatever you say minus m, or you can say m is here minus b, or I can say minus m equal to b. So if you plot this graph, then this is negative slope, m is equal to, so this is negative slope. So if you put that graphs, then what we get, y-axis is this, and x is root c, then what you get, that negative slopes. So negative slope is like this, and positive slope is like this. So here m is negative, so we put negative slope. So this is the graph for strong electrolytes. That's why we have drawn that. Also we have said that for strong electrolytes graphs will be like this, we have discussed, and it is already this, because strong electrolyte, that's why it is completely dissociate. So that's why lambda m previously, sorry, molar conductance previously it is very high value and very less amount has increases. Also we said that how this graph sets came, and this is given by Cole-Ansager equations. Okay, this is for strong electrolytes, because here slope is negative, slope equal to minus b. Okay, that is negative slope. Similarly, the graph of weak electrolytes, we says that it will come like this. So at first, whenever no dilutions we have done, then that molar conductance is very less value, and after that this value has increases. So how this graphs came, that also we can discuss. Let's say for weak electrolytes, what it says that Oswald's dilution law we have to discuss. So let's say if any weak electrolytes, any weak electrolyte if you take, let's say I am taking HA, then acid, let's say weak acid, then this will go to dissociate into H plus A minus, because this is weak electrolytes, so this is partially dissociate. And if T equal to 0, whenever you not did any reactions, let's say on that time concentration is there, then no dissociations occur. And whenever T equal to T equilibrium, so from here alpha will dissociate, because very less amount of dissociate, let's say alpha. So we already discussed about of this in chemical equilibrium and ionic equilibrium. So from here alpha will dissociate, so alpha we know that how much dissociate from this concentration. So C alpha means total is alpha, from alpha total is, suppose C concentration is there, from that it will dissociate alpha into C. Okay, this we already discussed in chemical equilibrium and ionic equilibrium. So if C is there, from that C alpha is dissociated and C alpha, so that is C minus C alpha. Okay, so in that solutions this is present, and we know that alpha is very less, that is less than 5% of C. So this amount of alpha is very less. So this alpha also we can say that molar conductance and molar conductance at infinity. Okay, and say here if I find that dissociation constant or equilibrium constant, then equilibrium constant is, what is the concentration of product divided by concentration of reactants. So K equilibrium, that is for dissociation, right, Kd is equal to concentration of product divided by concentration of reactants. Concentration of product at equilibrium is this and this. Not, you will not take the concentration, you will take the concentration at equilibrium, because at equilibrium is the stable state of the reactions, and in the solutions this is present, this concentration is present, which is in equilibrium. So concentration of product, that is C alpha into, so concentration, let me write H plus and A minus HA, this concentration. So H plus concentration is C alpha, and this is also C alpha, and then this is C minus C alpha. So if we this, I will reduce it. So Kd is equal to C alpha square, and this is C 1 minus alpha. So this we can cancel. Then this is equal to C alpha square 1 minus alpha, and we know. So if I take case 1, so most of the times alpha is very less than 1. So alpha is very less than 1. So if it is satisfied, then Kd will be, alpha is very less than 1, then 1 minus alpha is nearly equal to 1. So we will write C alpha square by 1. So we write C alpha square. So if we write, then alpha square equal to Kd upon C, and alpha is equal to root over of Kd upon C. And since Kd is constant, this is equilibrium constant or dissociation constant. So let's say this is 1, because that is constant, any constant value. So alpha is equal to this constant. So I will not take 1. So any constant value. So constant by root, that is, we assume as 1. Then this is become root over of C. Okay. So if we plot this equation, so we know that hyperbola, that y equal to 1 upon x, then yx equal to 1, then thus graph will be. So here this alpha, what you take as, so this alpha equal to this upon this, and whenever that C tends to 0, then alpha tends to 1. So if that molar conductance is increasing here and dilutions is increasing here, so whenever you dilutions means molar conductance is tending to 0. If molar conductance tends to 0, then alpha equal to 1. Alpha equal to 1 means this upon equal to 1, it means this equal to this value. So that means that whenever the dilutions increases means concentration decreases, on that time this value H increases huge amount, means tends to 1. So if I say this value is molar conductance and this by C, because alpha whenever C tends to 0, this by this, because alpha equal to this, so whenever this tends to 0 then alpha equal to 1, then this equal to this. So we can take this value of alpha as this value, then that is become 1 upon root C. If I take this as y and root concentrations as x, then this will be, we know that y equal to 1 by x, then yx equal to 1, that will give hyperbola. So this is the equations for weak electrolytes. So it not touch, because this is the graph of hyperbola, so it will not touch, it will go to infinity. Okay, this is the case 1. And for case 2, if alpha is comparatively more, or you can say not negligible, on that case what will happen? So we know that Kd equal to, what are the equations? C alpha square upon 1 minus alpha. So this alpha, because alpha is equal to this by this value, so I can put this value here. C, this is become 1 square okay. Then what I will do, this value become, so okay, so this value we will take as numerator, then this will become this. Okay, so this value will comes, so this C square upon this value. So if I do it, then what will come? So this will go to above, so this will become this value. So we can cancel it. Yes, so this will become upon this value. So here so if you do the graphs, this is equal to Kd. So if you put that graph, then what will do? Yes, so let's assume that Kd is equal to so this is the constant value. Okay, so let me see that actual picture. Okay, so this, so what you will do, you took the here C as here, then KD by 1 upon C is equal to, so if you put these graphs, let's say this is Y, let's say this is Y and this is X, this is, let's say, KD into 1 upon C. So here what you took, that 1 by C, so this is X if you took, then this will be slope. So here what that this value, you took, then this will be the straight line. So this will look like this, and this is slope is here KD. Okay, so we understand that for weak electrolytes that graph will this, and 100% and 99% alpha is very less value and it is negligible. So main case is case 1 is important and case 2 is not so important, because maximum case alpha is very less. So from that this graph is important. And for strong electrolytes this graph will come, and if you combine that strong electrolyte and weak electrolytes, what it says that combining of strong electrolyte that says for strong electrolyte graph comes something like this, and for weak electrolytes what it says that this can like this. So if you combine this, so here what happened now, that Karras laws he come into play, that Karras laws, what is in that for weak electrolytes we cannot get the for weak electrolytes, since this we cannot intercept on this molar conductance, so we will not get the value. But for strong electrolytes, if we extrapolate, then we can intercept with the Yx value. So whenever we combine these two plots, and this plot is okay. So this is the combinations of strong electrolyte and weak electrolyte plots. Okay, this is for strong electrolytes and this is for weak electrolytes. So in the next class we will discuss about of the Carus laws, how he used the strong electrolyte graphs to find the ions of weak electrolytes. So today we will discuss it today. After this, thank you.